Hello dear students, welcome to my channel. Today we have a special lecture on finding the numerically largest eigenvalue. So this is based on the eigenvalue problem, and basically we'll talk about power method. So finding the numerically largest eigenvalue by the power method. Now what is power method? Before that we have to know what is a eigenvalue problem. You know that eigenvalue problem is basically if we talk about a matrix a, a matrix A and its eigenvalues are lambda, then we are talking about this eigenvalue problem where lambda are the eigenvalues. And if A is a matrix, then you know determinant A minus lambda in is a n-dimensional nth order identity matrix equal to 0 is a characteristic equation corresponding to the matrix A. Then the roots of this characteristic polynomial are called the eigenvalues. So, power method is basically the method for finding the largest eigenvalue in magnitude and the corresponding eigenvector of the eigenvalue problem Ax equal to lambda x is called the power method. Let's have a look on that. What is the process? What is the methodology we are using? And with some examples. Now the question is, what is the importance of this method? The necessary and sufficient condition for convergence of the Gauss-Jacobi and Gauss-Seidel iteration while solving a system of equations is that the spectral radius of the iteration matrix H is less than 1 unit, that is rho of H less than 1, where rho A is the maximum of the modulus of the eigenvalues, maximum of the magnitude of the eigenvalues. That is your rho A. So that is your spectral radius actually. So where rho H is the largest eigenvalue in magnitude of H. If we write the matrix formulations of the methods, then we know H. We can now find the largest eigenvalue in magnitude of H, which determines whether the methods converge or not. So largest eigenvalue, that will give you the idea the method will converge or not. So let's start the process. Let lambda 1, lambda 2, etc. lambda n be the distinct eigenvalues such that modulus of lambda 1 is more than the modulus of lambda 2 is greater than etc. So mod lambda 1 is the largest among all the eigenvalues. Modulus, talking about the magnitude. Let v1, v2, vn be eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, lambda n, etc. respectively. The method is applicable if a complete system of n linearly independent eigenvectors exist. N linearly independent eigenvectors exist. And this idea of linear independence of the eigenvectors came from the vector space, the concept of vector space. In those chapters, linear algebra, you have learned about the concept of eigenvalues, eigenvectors, their independency, dependency. Even though some of the eigenvalues may not be distinct, maybe some of the eigenvalues are similar, no problem. Then n linearly independent eigenvectors from an n-dimensional vector space. Okay? Any vector v in the space of eigenvectors v1, v2, vn can be written as a linear combination of these eigenvectors. That is, v vector equal to c1 v1 vector, c2 plus c2 v2 vector plus cn vn vector. So any vector v in the space of the eigenvectors v1, v2, vn can be expressed as the linear combination of this vector, and this is the linear expression 1.2. It should be 1.2, not 1 comma 2. It is 1.1, equation number 1.1, typographical error. Okay. Now, pre-multiplying by a and substituting. So what I'm doing, I'm pre-multiplying the equation 1.2 by a and substituting a v1 equal to lambda 1 v1, a v2 equal to lambda 2 v2, etc., and a vn equal to lambda n vn. We obtain av equal to c1 lambda 1 v1 plus c2 lambda 2 v2, etc., cn lambda n vn. And that's equal to lambda 1 c1 v1 plus c2. So what I've taken, lambda 1 is the maximum magnitude. Lambda was having the maximum magnitude. So I'm taking this one common. So it will be, and obviously it is non-zero. So it will be lambda 1 close bracket c1 v1 vector, c2 lambda 2 by lambda 1 v2 vector, etc. Similarly, cn lambda n by lambda 1 vn vector, close bracket. Okay. Now this is the first. So what I'm doing, I have done pre-multiplying by a and substituting these values. Now again, pre-multiply by a, this equation. So it will be a square b. A square is a matrix multiplication, a times a. And this one will be, again you are substituting these values. And simplifying, you will get lambda 1 square. So you are taking lambda 1 square common. So lambda 1 square, lambda 2 by lambda 1 whole square, v2 vector, etc. cn lambda n over lambda 1 whole square, vn. Okay. This is again you are multiplying with a, and continue with the process, and so on. Lastly, if you are multiplying the matrix A by k times, then it will be a to the power k v and lambda 1 to the power k, and this power will be k. All the powers will be k, and the similar expressions you have. This is 1.3. Okay, equation 1.3. Now, also we have, again you are multiplying with a. That means I want a k plus 1 times multiplication. So you have an equation, the similar expression, you look at that, and you have 1.4. Equation 3, 1.3 and 1.4. So only difference between 1.3 and 1.4 is that there is a power k plus k and k plus 1. That is the difference. Okay. Now, as k goes to infinity, the right hand side of 1.3 and 1.4 tends to this one. Why? Because you see, lambda 1, modulus of lambda 1 is more than modulus of lambda 2, right? So naturally, your lambda 2 by lambda 1 must be less than 1. Its magnitude must be less than 1, right? And something to the power k, if k goes to infinity, this goes to 0. These values will be 0. The terms will be 0. That is the advantage of the method. And that is the beautiful nature of the method. So these values will goes to 0 because magnitude it is less than 1. So all the terms will be 0. This term will be 0. This term will be 0. Only you are remain with the first term, that is lambda 1 to the power k c1 v1 vector. Look at that. Okay. And in the second term, second 1.4, equation 1.4, the similar expression. The lambda 2 by lambda 1 is numerically less than 1. Their magnitude is less than 1. So their power goes to infinity. Then it will goes to 0. The values goes to 0. So this will be 0. This will be 0. So you have remained with the first term only. Lambda 1 and k plus 1 c1 v1. This is the thing. Now since, oh yeah, this is the explanation. As I have explained, this is numerically less than 1. Now, the vector C1V1 also tends to C1V1 vector, which is an eigenvector corresponding to lambda 1. Okay, look at that, this one. Yeah. So this one C1V1 plus C2 lambda 2 by lambda 1k, this all goes to tends to C1V1, which is the eigenvector corresponding to lambda 1. Now, next, the eigenvalue lambda 1 is obtained as the ratio of the corresponding components of the matrix AK plus 1 and the vector V and AKV. That is, lambda 1 equal to limit k tends to infinity. This ratio AK plus 1 B V suffix R and AKV suffix R are equal to 1 to n, etc. So you will get the eigenvalue lambda by this ratio. I will show you in the problems, where the suffix R denotes the rth component of the vector. Therefore, we obtain n ratios. If you have n components, you have n ratios. All of them tending to the same eigenvalue, which is the largest eigenvalue in magnitude. So you have n ratios, my dear students, and all of them tending to the same eigenvalue, which is the largest eigenvalue in magnitude. And now the question is, when do we stop the iteration? The iterations are stopped when all the magnitude of the differences of the ratios are less than the given error tolerance. Then you stop. In that case, you will stop. You have to stop. Okay? So this is the process of finding the numerically largest eigenvalue by power method. Now some remarks. Now the choice of the initial approximation vector V0 is very important. Otherwise it will diverge. If the choice is not correct, it will go far away from your initial point. If no suitable approximation is available, we can choose V0 with all its components as one unit. That is V0 equal to 1, 1, 1, 1, 1. Like this. If no suitable approximation is available, you can't find any suitable approximation, neither in your problems it is given. So don't worry about that. You just have to select a unit vector. All the components are 1, 1, 1. However, this initial approximation to the vector should be non-orthogonal to V1. It should not be orthogonal to V1. It should be not orthogonal to V1. This is important thing. Next is faster convergence is obtained when, this one will be 1. This is also typographical error. This one will be 1. If lambda 2, modulus of lambda 2 is much less than lambda 1. Okay. Much less than lambda 1. This is lambda 1. Modulus of lambda 1. So if lambda 2, modulus of lambda 2 is much lesser than lambda 1, then faster convergence is obtained. In order to keep the round of errors under control, actually what we are doing, you are dividing, multiplying. So a lot of things are happening. So there will be round of errors came into the picture. So we normalize the vector before pre-multiplying by A. The normalization that we use is to make the largest element in magnitude as unity. So what is the normalization? The normalization that we use is to make the largest element in magnitude as unity. That's it. Now, if we use this normalization, a simple algorithm for the power method can be written as follows. So whatever we have learned, we can concise our concept and we can have few steps, simple algorithm. You can use a programming for that. So yk plus 1 is a vk matrix, and this is the vector, eigenvector. Vk plus 1 is yk plus 1 over mk plus 1, where mk plus 1 is the largest element in magnitude of yk plus 1. Then lambda 1 is limit k goes to infinity yk plus 1 r by yk r equal to 1, 2, 3, etc. And vk plus 1 is the required eigenvector. It may be noted that as k goes to infinity, mk plus 1 also gives lambda 1. So this is the simple algorithm in a very compact form. Now let's go to the problems. Let us start with a very simple problem. Determine the dominant eigenvalue of lambda by the power method. 1, 2, 3, 4. The simple matrix, simplest form. So no initial guess is given here. So let us assume that. Let me solve in a different page. Yeah. So the matrix is A 1, 2, 3, 4, right? And suppose the initial approximation be taken as 1, 1. Okay. So this is the column vector. Now y1, let me write y1. You check the simple algorithm. I will follow the simple algorithm. So if k is 0, the 0th iteration, that is y1 equal to av1, right? So y1 equal to av1. What is your A matrix, my dear students? Oh, av0. Okay, 0, because k is 0, 0th iteration. So I have taken k equal to 0 for k equal to 0, right? This is first iteration. So A is 1, 2, 3, 4, and v1 is v0, sorry, v0 is 1, 1. So you have, if you do this, you have 3, 7. Quickly you can check, this is 3, 7. And so the largest magnitude, m1 is the largest of them, so that is 7. Magnitude is greater. You look at that. mk plus 1 is the largest element in magnitude of yk plus 1. So this is your y1. In y1, m1 is 7 because 7 is the largest magnitude. So now you will write v1. What is your v1? v1 is, look at the formula. v1 is y1 by m1, right? y1 over m1, okay? So m1 is 7, 1 by 7. Let me write, what is your y1? y1 is 3, 7, okay? And that will be equal to, if you divide 3 by 7, so that will be, I have calculated, so I'm writing the data, writing the values, so you can cross check that. 1. So this is your v1. So you have calculated y1, v1. This is your first iteration. Let's come to the second iteration, that is for k equal to 1. For k equal to 1, you have y2. y2 equal to a v2, right? What is your A? A matrix is 1, 2, 3, 4. And what, sorry, this is your v1. This should be your v1. So what is your v1? v1 will be 0.42857 and 1, okay? And calculate this one. If you calculate, and I'm telling you the result, I have calculated already. So 2.42857, okay, and 5.28571. Clear? This is your y2. Again, what is your m2? What is m2? m2 is this one. This is numerically, this is larger. So magnitude, greater magnitude, 5228571. Okay, this is m2. Now calculate v2. What is your v2? That is your y2 by m2. Okay, m2 is this one and this is your y2. So if you divide inside, you will get 0.459496, and you have a 6. This one you can calculate. This is your y2, this is your y2, and this is your m2. So you divide the elements inside y2 by m2, you will get this result. So this is, you have calculated the second iteration, y2 v2 k1. Now the next iteration for k equal to 3. So you will calculate y3. Okay, y3 will be a v2. Okay, a v2. Look at that. You have calculated like this, and you will have m3. If you calculate, in this case you have m3. You have m2 earlier, now m3. m3 will be 5.37838. Okay, now what is your v3? v3 will be y3 by m3. That is equal to 0.457291. Okay, this is your v3. This is your third iteration, and so on. Let me write the last. That is, I have calculated this one. I will go to the conclusion. v5, I'm not calculating v4 once again. You can calculate similarly. You will go for k4, you can calculate k6, so on, as per your requirement. Let me tell you why v5 is your y5 by m5, m4, sorry. v5 is your m5, sorry, m5, y5 by m5, and that will be equal to 0.45743, and this is 1. And y6 is a v5. Okay, that is equal to, if you write 2.45743 and 5.37229. Okay, so this is your y6 and v5. Now I will find the ratios. I will show you how to calculate the ratios. That is why. Sorry. Yeah, got it. Now find the ratios. So ratios will be lambda 1, limit k tends to infinity, vk plus 1. I'm writing the formula first. K plus 1. Sorry. K plus 1 r by vk. Look at the formula. Here you have a formula. Yeah. Yeah. That's it. Yk plus 1. This should be vk. Yeah, there is another typographical error. This should be vk. This should be vk. Vk. Your denominator should be vkr. This actually same thing. Y came here. So here also, I guess, yeah, this is fine. No problem. But this should be your vk. So you have here also yk plus 1 by vk. Okay. Now, what is your r equal to 1, 2? Because you have two components only. So you have two ratios. So what is your y6? So this one. This divided by your v5 will be this. y6 by v5. Okay. So I will divide I will write 2.45743 by 2.45743 by 0.45743, 0.45743. Okay, and the next ratio is 5.37229 by 1, and that will be 5.37229, 5.37229 by 1. So that will give you this lambda 1. Both are lambda 1. Both are lambda 1. Okay. So this using the formula yk plus 1 by vk, that is y6 by v5 for 2 are equal to 1, 2, because you have two components. Okay. Clear, everyone? This one and this one. Now, if you calculate this one, you will get 0.53, 5.3, okay, sorry, it will be 5.37225, and this one is 5.37229. So you have two values very close. Okay. Now, so this will be, suppose you want the lambda 1 correct to 4 decimal place. So this will be the answer. You see, 5.3722 up to 4 decimal places, or nearly about, you say, 4 significant figures, 5.372. You want to write 5.372, 4 significant digits you have. This is your answer. This is the numerically largest eigenvalue by power method. Now, if you want to calculate the error, so error is this minus this, 5.37229. So if you want to calculate the error, 5.37229 minus 5.37225, and that will be equal to 0.404, and that is less than 0.405. Okay, so hence the dominant eigenvalue. So this is the error calculation. Error is much less than the specified thing. So your dominant eigenvalue correct to 3 significant figures or 4 significant figures is given by 5.372. That's the power method, my dear. It's a very simple method, but you have to do a lot of calculations, a lot of iteration steps, and you have to go for 3 cross 3 matrix. The calculation will be more. So you have a problem. Lastly, in my last presentation, this is the problem you have to do. Determine the eigenvalue, numerically largest eigenvalue, and the corresponding eigenvector of the following matrix using the power method. Okay, everybody. So I hope this lecture will be helpful to you, and follow my lectures in my channel. Share my videos with your friends, relatives, and subscribe my channel. Thank you, all of you.